Hi, everyone. The other day, I put together a blog posting of exploratory factor analysis of items from the epistemic belief inventory, where I used RStudio and EFA.dimensions. And you can actually find that posting at this link right here. I'm going to include this link underneath the video description. So if you go to this particular posting, you're going to see a breakdown of, the items from the EBI that I carried out the factor analysis on, and then also the how-tos in terms of, the steps involved in carrying out factor analysis, kind of generally the decision process, as well as different analytic approaches to addressing questions at each of those steps. And then you'll also see too an overview of the interpretations I offer with respect to the outputs that are generated. So I encourage you to go to this particular website right here in order to kind of learn more. If you want to learn more about EFA dimensions, this would be a good place to go. In addition, what I want to do in this particular video is just show you the basics in terms of getting the data into RStudio and then running those analyses. Just for those folks that prefer a little bit more of a real-time discussion of how to create the code and so forth to carry out the analyses. That's what the main purpose of this video is. So the data is actually saved to an Excel file. The data is based on data that you would find at this website right here. This article is entitled Three-Factor Structure for Epistemic Belief Inventory, a Cross-Validation Study. This is at the +ONE website, and the authors provided their raw data so that we could, we can reanalyze it. And I'm just using a subset of this data. And so if you'd like to download a copy of the data to follow along with the blog posting or with this video, you can download it right here. I'll also include a link underneath the video description for that. So here we are in RStudio, and again, the data has been is already in an Excel file. It's saved on a location in my computer. So I'm going to start out just by going to Session, go to Set Working Directory, choose Directory, and then go to the location on my computer where the data would be housed. So it's actually housed under a folder that I've called EBI. So I'm going to click on Open right here and then import the data by going to File, Import Data Set, go to From Excel, and then right here, we'll just click on Browse, and here's our data set. So it's EBI data S1B. The S is in caps. So we'll click on Open and finish the importation process. We'll click on Import right here. And so now we have our data set that's been imported, and it's saved to a data frame that is called EBI data S1B, with, again, that S being in caps. So the first thing that I do in the blog posting, though, is I actually create a separate data frame that contains just the variables that I'll be subjecting to factor analysis. So to do that, I'm going to go to File, click on New File, and we're going to go to the script editor, our script. And this is where we will actually be typing all of our commands. So the first step at that blog posting is just, it's in the preliminary section. I'm going to create a data frame. I'm going to call it item data with an arrow. That's just basically a less than sign followed by a hyphen. Then type in EBI data S1B with that S being in caps. Then from there, I'm going to type a bracket. Inside, I'll type a comma and then use the C function. And here what we're going to do is we're going to refer to the columns in our data set that, basically referring to the variables that we want to save to this new data frame. But we're referring to the column number, not the actual names of the variables. So if you go into under here, under this tab, you'll see we've got CE1, CE2, CE3, all the way to CE5, then and so forth. So all of those, the numbers are actually associated with those columns right there. But when we're referring to the columns in our code, we're going to actually be referring to the column number and not the name. So I'm going to go back under here, and we are going to be using the variables or the items in columns 1 through 5. So I'm going to type 1:5, then comma, we'll refer to the variable or item in column 8, So I'll type an 8 right there, then comma, then 9, comma, 11, comma, 14, comma, 15, comma, 17, comma, 20, comma, 22, and then 24 colon 27. So getting those four items as well. So now you'll see that we have an in parenthesis, which basically is closing out the C function right here, and then in bracket right here that you see. And so if I highlight all of this and click on the run button, you'll see that basically this data for these variables is all saved to this data frame. So if I go down and I type in str, then item data, then in here, if I highlight this and run it, you'll see I've got a breakdown of those variables or items. So I've got CE1 and then CE1 through CE5, then 8, 9, and then ultimately item 27, and all those are registering as numeric. So the next thing in that blog posting, though, is I start to use the library function to call up the EFA dimensions and the psych package. We only use the psych package just for a second there to generate correlations among our items. And really, after that, it's all going to be using the EFA.dimensions package. So if you haven't already done so, you're going to need to install the packages. You can just use the install.packages function. Inside quotation marks, we'll type in EFA.dimensions right here. Make sure that those, again, are in quotation marks, and those are enclosed inside parentheses. We can also do install.packages, and then quotation marks, then psych, in quotation marks, in parentheses. So if you highlight both of those and you run that, then it will basically just open up both of those packages, or excuse me, install those packages, and then we can use the library function to call them up. So this part is actually not shown in the blog posting, but I just wanted to show you. We're going to start with the library function then, because now these have both been installed. We'll type in library EFA dimensions, and then library, then psych right there. So if I highlight both of these, click on the run button, basically it's going to, RStudio is going to unzip both of those packages. And so the functions associated with those are ready to be used. So the first thing that we're going to do is we're going to type in core.test, and we're going to refer back to our data frame that contains just the items that we are factor analyzing. So it's this item data object right here. So I'll type in item data and then comma, and then we'll type in use equals quotation marks complete period OBS for complete observations, and then in quotation marks, and then obviously in parentheses. So what is going on right here is we're using this function that's associated with the psych package in order to generate the inter-item correlations among for our items, and then we can use that as a partial basis for evaluating whether or not it makes sense to carry out a factor analysis of our items. So think about it this way, that basically with factor analysis, the objective is to identify latent variables or hidden dimensions, if you will, or factors that account for the intercorrelations among a set of measured variables, or in our case, items. And so if there are really very low correlations, near zero correlations among our variables or items, then it makes a lot less sense to carry out the factor analysis, because there would be no latent variables or factors that would account for essentially the non-relations among those variables. So what we want is there to be substantial correlations in our correlation matrix. But by the same token, we also don't want to have correlations that are so high that can produce either improper solutions or perhaps even causing algorithmic problems where you can't actually carry out the analysis, such as in the case where you might have singularity in your correlation matrix. So starting out by looking at the correlations using the core.test function, it can be useful. So we're going to highlight this and click on run. and we get our correlation matrix right here. So the correlation matrix just contains all of the basic info that you would see in any standard correlation matrix. Basically, just keep in mind that along the principal diagonal, all of these values are going to be 1, and all the way down to the last item, as you can see right here. It's and then you'll see that there are basically two triangles. There's an upper triangle and a lower triangle. The values in the upper triangle are the same as the values in the lower triangle. Okay, so you can just basically use, either the upper or lower triangle when you're trying to kind of identify correlations that are indicating more substantial relationships or perhaps problematic correlations. So just as a general rule, what you're looking for, or at least some correlations in your correlation matrix that are 0.30 or greater in absolute value. So that's ideally what you would see. And so there's about 10 of them in this particular correlation matrix, which is a good thing. It's not really, a lot of the correlations aren't as high as one might hope, but there's still a fair number of them that sort of meet that threshold. And by the same token, you also are looking for correlations that might be 0.90 or above, that might signal some problems with collinearity and possible singularity. So we don't want to have that kind of situation either. And it turns out that none of the correlations in our matrix appear problematic in that respect. So then the next function that we're going to use, and the remaining functions, are basically associated with the EFA.dimensions package. So the first one is the factorability function. So we'll type in factorability, and I'm just going to kind of highlight it right here, and we're going to refer to our object, our data frame that contains our variable information. So we'll type in item data right here. And so what this is going to do is generate several additional indices and tests for evaluating whether or not it makes sense to carry out a factor analysis on these items. So if I highlight this and click on run, we'll just kind of take a quick look at our output. You'll see first off, you'll see information in the form of the determinant of the correlation matrix. So the determinant of the correlation matrix, you can kind of basically look at it as a generalized variance. And what you don't want to have is a situation where the determinant is 0. Okay, so and in fact, what as is kind of given in this particular output right here, it's saying the determinant of the correlation matrix should be greater than 0.00001. Okay, so the determinant in our correlation matrix is 0.113, which is obviously greater than that number. So that's a good thing in terms of the factorability of the correlation matrix. If we happen to have a situation where it was actually 0 or basically less than that number, then we run into problems with singularity of the correlation matrix, and it can produce problems in terms of carrying out our analyses. You also have the Bartlett's test over here. So this is Bartlett's test. It's a chi-square test. So there's the chi-square value, degrees of freedom, and the p-value right there. And so Bartlett's test is basically testing whether your correlation matrix is different from an identity matrix. And an identity matrix basically has ones along the principal diagonal, zeros on the off diagonal. And so the identity matrix, it would be consistent with a correlation matrix where there are no correlations, or the correlations are effectively 0 among all your items. So in this case right here, we find that Bartlett's test is statistically significant. So that's actually a good thing in terms of the factorability of our correlation matrix. Another index that you're going to see, kind of scroll down a little bit below, you'll see that we've got the Kaiser-Meyer-Olkin measure of sampling adequacy, or MSA. And so there's actually the kind of overall MSA as well as item level MSA. And just in terms of some guidelines, in terms of thinking about the sampling adequacy, if you will, you have Kaiser and Rice's interpretation guidelines provided in the output. So basically what you're looking for are MSA values that are going to be definitely above 0.5. If you have an overall MSA that's less than 0.5, then in that particular case, really factor analysis is not going to be something that you want to do. So, the KMO MSA, if it's less than 0.5, would be considered unacceptable for factor analysis. And then they kind of give you these flowery labels for different ranges that you see right here. So you got MSA values in the 0.5s would be considered miserable. Then you got mediocre, then middling in the 0.7s, meritorious, and marvelous. Marvelous being 0.9 or above. So in terms of our MSA value, you can see it's 0.78 overall. So that's actually puts us into the middling range, but that's still sufficient for carrying out our exploratory factor analysis. If you scroll up and you look at the variable MSAs right here, what you're again looking for are values that are going to be above 0.5, basically above 0.5, really ideally above 0.6. And so in all these cases, though, the lowest MSA value is actually going to put us in at about 0.67, which would suggest then that all the items are reasonable for carrying out the factor analysis. If you happen to have an item that's not, meeting at least a 0.5, perhaps a 0.6, just depending on your tolerance level, in that particular case, that would be grounds for possibly removing that item before carrying out the factor analysis. So overall, what we have is evidence of at least that's reasonable to carry out our exploratory factor analysis. So then the next step along the way, basically what we want to do is to determine the number of factors or come up with an estimate of the number of factors that may explain the intercorrelations among our items. Okay, so that's kind of the next big step in the process. And so once you've made that determination, then ultimately what you end up doing is you rerun the analysis, forcing that particular solution, rotating the factors, and then interpreting them. So in this next step where we're trying to determine the number of factors, we're going to kind of just walk through some of that code that's provided in the blog posting. So the first function that we're going to use is the raw PAR function. So this is for carrying out a parallel analysis, and really loosely stated, what we're doing is we're computing eigenvalues from our raw data and computing random eigenvalues or simulated eigenvalues, and we're making a comparison between the two, and we retain the number of factors that have eigenvalues from our raw data that exceed those from the random eigenvalues. So what we'll do is we'll first type in item data, which is the name of our data frame again, then comma, we'll type in factor model, set that equal to, and you have two options. You have either PCA or PAF. PCA is for principal components analysis. PAF is for principal axis factoring. So I'm going to use PCA in this one right here. That's actually the more long-standing approach to carrying out the analysis. Basically what it entails is generating components from an unreduced correlation matrix, which I talk about in the blog posting, and essentially comparing those against those random eigenvalues. The PAF is essentially extracting factors from a reduced correlation matrix, and so there's a difference there. And there's some debate in the literature about whether you should use PCA or PAF. Like I said, right now we're going to stick with the more long-standing approach. So we'll type a comma, then in data set, the N being in caps, and then we'll type in 1000. And actually, I should say in data sets right there. We'll set that equal to 1000. So we're going to generate 1000 sets of simulated or random eigenvalues. We're going to also use the percentile argument right here and set this equal to 95. So there you go. So if I highlight this and click on run, takes a few seconds, but then it generates our output. So you'll notice in our output, it says extraction method, principal components. There are 17 variables. The number of cases in our raw data was 1,039. The number of data sets that were generated, basically those data sets are generated with the assumption that our items are uncorrelated. Okay, and then we extract a complete set of eigenvalues from each of those correlation matrices, and then we can compute the mean of those or the 95th percentile, and those are the random eigenvalues that can be compared against the eigenvalues from our data. So if we scroll down a little bit further, you can see that we have the real data eigenvalues contained in this column. They're the mean eigenvalues, and then the 95th percentile eigenvalues shown here. And I'm going to stick with comparing the eigenvalues in the 95th percentiles against the real data eigenvalues that you see here. So as you can see, for the first factor, the real data eigenvalue is 3.059. The random eigenvalue is 1.268. The second factor has an eigenvalue of 2.042. The random eigenvalue of 1.213. So that's exceeding the random eigenvalue. For the third eigenvalue is 1.427. And comparing it against the random eigenvalue of 1.174. But then on the fourth factor, you can see that the eigenvalue is 0.998, which is less than the eigenvalue for the 95th percentile of those randomly generated eigenvalues. So that would suggest then that we would retain a three-factor solution. So that's one estimate of the number of factors that may account for the relationships among our variables. So just showing you the second approach, if we wanted to use it, we can use raw PAR and then item data, then factor model is equal to, and then quotation marks PAF in quotation marks, then comma, then we'll type in data sets, set that equal to 1000 again. We'll type in percentile, set that equal to 95. And if we do this, click on run, you'll see that in this particular case, it actually suggests a four-factor solution might be tenable. So the previous one suggested three factors, and you can even see the little recommendation down here for three factors. And then this one actually suggests four factors. So keep in mind too that when you are trying to determine the number of factors, these different methods, they don't all necessarily agree. And so you should be thinking in terms of, which of the approaches are better in terms of determining the number of factors, which are kind of less prone to overfactoring or underfactoring, that sort of thing. And then also considering too the interpretability of any solution that you generate at the end, so any rotated solution. So right now we've basically got two approaches that are suggesting, one suggesting three factors, the other one suggesting four factors. The next approach is going to be using the map function. So we'll type in map, and then inside parenthesis, we'll type in item data here. So when we highlight this and click on run, we can generate the results from the map test. And again, all of these are discussed in the blog posting, so be sure to check that out. So we'll scroll down. We've got Velliser's average squared correlations, and really what we're looking for is at the values in this column right here, and where it says root, basically you'll see the first root, it says 0. Basically that is where no components have been extracted, and we have that value right there for the average squared correlation among our items. Then we've got root 1 right there. This is basically what the value that's given here is the partial correlations among all the items after factoring out or controlling for the first component, the first principal component. And then for the second principal component, that would be the value that you see there, and so forth. So what we're looking for is the smallest value in this particular column, and that's going to signal the number of factors that may account for the interrelations among our variables. And so as you're looking at this, you'll see that down here at the very bottom, it says the smallest average squared correlation is 0.01315, which is this number right here. And so that's actually suggesting then a one-factor solution. And so you can see too, they even give you that little description right here for the map test. So we're using that so in that particular case, now we've got a 1-factor solution that might be suggested, a 3-factor solution, and then also a 4-factor solution. So when we scroll down a little bit further, we'll also add some more code in here. So at this point, we're going to type in scree-plot. So we'll type in scree_plot, and then inside our parenthesis, we'll type in item data as well. So now we can generate a scree plot, which is basically a plot of the eigenvalues from a PCA solution against a component number. So I'm going to kind of move myself up there just a bit there, and we'll highlight this and we'll click on run. And so now you can see that we have our scree plot. So as you're looking at the output on the left, you'll notice that we've got, it says eigenvalues. And so basically these are the eigenvalues from a principal components analysis. And those values that you see in this column right here are the ones that are plotted on the y. They're basically shown on the y-axis in the plot on the right, and then they're basically plotted against those different roots, which are basically different components. We can actually kind of stretch this out just a little bit more so you can get a better picture of it. And so when you're looking at this, what you're looking for is kind of an elbow. So if you think about all of this area up here, and just highlight it right here. All of this area up here, it looks like the side of a mountain. And then you've got kind of the rubble at the base of the mountain at the bottom. So what we're looking for is kind of an elbow where it sort of makes the break between the more dominant factors, if you will, and the rubble at the base of the mountain, more trivial factors. So this would be kind of the location of the elbow. It looks pretty clear that starting at this point, the rubble begins, so to speak. So what that would suggest then, looking at this particular plot, is that we have a 3-factor solution. So that's suggesting 3 factors, again, alongside our parallel analysis, which also suggested 3 factors. So we've got 2 pieces of evidence that are actually suggesting a 3-factor solution may be tenable. Then we've got a 1-factor represented by the map test, and then also 4-factor represented by a parallel analysis using the principal axis factoring extraction. So the next thing that we're going to do is kind of go down a little bit more, and we'll type in SMT. And really, to tell you the truth, I'm not a strong proponent of this approach, but basically what this is going to do is this is using, this basically involves computing chi-square goodness of fit tests for different factor models. And so I'm going to type in the name item data right here, and what we're doing is we're making comparisons among different models in terms of their fit, and then we essentially are trying to pick the model that has the best fit with the fewest number of factors. That's kind of the idea behind it. The problem with this particular approach is it's very heavily impacted by sample size. In our factor analysis here, we actually have 1,039 cases, which means that really even if we did have a good fit, a model that theoretically would be a good fit to the data, is more likely to be significant, which would be suggesting poor fit. So just to show you what I'm talking about, though, we'll highlight this and click on run. And so now you can see that we have these chi-square tests. These are sequential chi-square tests, right up here. And so you'll see it says number of factors, and then you've got, a 1-factor model, a 2-factor model, 3-factor model, all the way through 8 factors down here. And in terms of the test itself, what we're looking for is the model where the p-value is indicating non-significance. So basically with these chi-square tests, any model where you have a significant chi-square value, that would be indicating that you have a significant deviation from good fit. That's actually considered an indicator of poor fit. Whereas if you have non-significance for that particular test, then that's signifying good fit, or at least acceptable fit. So you'll see that in terms of this, the 8-factor model, that's the only one that is non-significant at the conventional 0.05 level. So using that particular approach, this would actually suggest an 8-factor model might be an adequate representation of the correlations among our measured variables. And that's obviously that is a lot of factors to be considering. And in fact, given what I was just saying before about these tests being particularly influenced by sample size, and given our very large sample size, I'm not apt to trust this particular recommendation. So next, we're going to move on to another option that's available in the EFA.dimensions package, and that is the empirical Kaiser criterion. So basically, we can use the function EMPKC, and inside parenthesis, I'll type in item data again, and we'll highlight this and click on Run. Oops, let me highlight that one more time, click on Run. And so then we get our output. So what we have right here, we have our eigenvalues. Again, these are basically from our from a PCA solution right here. And if you were using the standard, the old traditional Kaiser criterion, that's the eigenvalue cutoff rule. And the idea is that after subjecting your data to a principal components analysis and computing the eigenvalues for those principal components, you retain those components with eigenvalues that are greater than 1. And then that would serve as your estimate of the number of factors. So if we were just using that particular approach, you would see that all three of these component solutions, all those eigenvalues are greater than 1. But if you move to component 4, then that value is less than 1. So that would actually suggest then three factors may account for the interrelationships among our variables. So if we're using the standard Kaiser criterion, that particular approach has been known to oftentimes produce overfactoring. There are various issues with this. It's been hotly debated in the literature. It's generally not recommended as a basis for deciding on the number of factors. But there is this empirical Kaiser criterion that I discussed a little bit in the blog posting, and basically what we are doing is we are comparing these reference values against the eigenvalues from our data, and we're using a similar logic to what we had before with respect to parallel analysis. We're comparing these reference values against the eigenvalues, and then we retain those factors that have an eigenvalue from our data that exceed those reference values. So you can see that for the first eigenvalue right here, it's greater than the reference eigenvalue. For the second one, it's greater than that reference value right there. For the third one, it's also greater than that reference value. And then for the fourth one, it's actually less than. So in this particular case, it actually turns out that the empirical Kaiser criterion gives us the same suggestion as if we had used the original Kaiser criterion. But just keep in mind that that original is extremely problematic. And so this is actually a better approach when it comes to deciding on the number of factors. So now it's suggesting down here that the number of factors is 3 factors. So now at this point, we've kind of looked at these different ways of determining the number of factors. And so you can see that we've got actually 3 different approaches are suggesting a 3-factor model. We had one that suggested a 1-factor model. Really, that 1-factor model is not particularly tenable from a theoretical standpoint. The scale that we were factor analyzing is an epistemological belief inventory or epistemic belief inventory, and those beliefs are generally regarded as multidimensional. So a 1-factor solution just does not seem very reasonable in that particular case. The 8-factor solution that was suggested by the sequential chi-square test also seems to be particularly problematic. So we have a couple of options. One is a 3-factor model, and the other one being a 4-factor model. I'm going to actually stick with going with a 3-factor model as I do in the blog posting. But in reality, what I might do is to run the 3-factor model and then run the 4-factor model and then see, do we have problems in terms of interpretation of the factors that are retained and rotated using those different approaches, and also do we have enough items that help to define those factors, and so we could compare those different solutions. But for this particular presentation, both here in the video and in the blog, I'm going to mainly focus in on the three-factor model. So what we're going to do then is we're going to add another line down here. And at this point, we are going to use the function PA_FA. So this is also associated with the EFA.dimensions package. So I'm going to type, create my little parenthesis here and type in item data. So we're going to refer back to that again. Now we're going to type in core kind. So COR kind, set that equal to, and then inside our quotation marks here, we're going to type Pearson, because we're analyzing a correlation matrix containing Pearson's correlations. So then from there, we're going to type comma, and then n factors, with the n being in caps. So n factors, we're going to set this equal to 3, because we're going to basically, now that we've sort of decided upon a three-factor solution, we're going to force that factor model, and then we are going to rotate those three factors so that we can interpret our factors. So next, I'll type a comma. I'll type an ITER PAF. So this is basically iterated principal axis factoring. And the number of iterations, we're going to set this, I'll just go ahead and set this equal to 50, then comma, and then we'll type in rotate. And we'll set this equal to either, a type of orthogonal or oblique rotation. For the first part of my blog posting, I use Promax rotation, which is an oblique rotation. So I'm going to type quotation marks here, and then we'll type in Promax in all caps. Okay, so at this point, we'll highlight this, click on run, and we get our output. So just kind of scrolling back up here at the top, you'll see there's a lot of output that's been generated. You'll notice that we have a table containing initial communalities and extraction communalities. So the basic idea in principal axis factoring, where it starts, is with an initial estimate of communality. The initial communalities are basically computed as the squared multiple correlation between each item and the remaining items in our scale. So if you think about it as regressing each item onto the remaining items and computing the R-square value, these are essentially R-square values. And these values are initially input into the principal diagonal of the correlation matrix that's being factored. Then through an iterative process, we have we arrive at an ultimate extraction of our factors, and then we end up with communalities, extraction communalities. And these are the communalities. Basically, you can interpret them as the proportion of variation in each of our items that's accounted for by the complete set of extracted factors. So like for the CE1 variable right here, or item, basically the three factors collectively account for about 21% of the variation. Then for CE2, the factors account for about 31% of the variation, and so forth. If we scroll down a little bit further, this part of our output right here, believe it or not, this is just basically from a principal components analysis. So these are the same eigenvalues that we had seen previously. So there's not really a whole lot of additional information to be gained by looking at this particular part of the output. We'll scroll down. You'll see also a little bit of detail here where it says PAF. Our principal axis factoring converges in 9 iterations. That's just letting you know that. We'll scroll down a little bit further, and then we end up with our unrotated factor loadings and the eigenvalues for those factors and variance accounted for. So you'll see we have unrotated principal axis factor loadings. This is just basically the unrotated pattern matrix. The loadings that you see in here are just basically correlations between each of the items and the factors. If you scroll down a little bit further, you've got sort of a breakdown of the eigenvalues following rotation. So you'll see you've got the 2.34 for factor 1, 1.35 for factor 2, and 0.7 for factor 3. And then you've got the proportion of variance accounted for in the original set of items that's accounted for by each of those factors, as well as the cumulative proportion of variance as well. So all of these are described in the blog posting. I'm trying to kind of keep this reasonable in terms of timing, so be sure to go there. But really, under most circumstances, folks don't spend any time really interpreting the unrotated loadings, because a lot of times they're just, quite frankly, uninterpretable. So what we typically do, though, is we interpret the rotated loadings. And when I say interpret those loadings, what we end up doing is trying to kind of give naming or meaning to the factors that have been extracted. So what's happening is that we've extracted a set of factors, and then we rotate them in order to facilitate interpretation of them. And so if you scroll down a little bit further, now you'll see that we've got a Promax rotation pattern matrix, and then also a Promax rotation structure matrix. So in terms of naming our factors, you'll want to use the Promax rotated pattern matrix. You can use the structure matrix to kind of supplement, but you mainly want to focus your attention in on that pattern matrix. So again, I'm going to defer to the blog posting for most of the heavier discussion. There's a few points in there that I wanted to communicate a little bit better through writing than trying to talk through it all in this particular video. But I will say that in a nutshell, factors 1, 2, and 3 roughly correspond to the three factors that the authors found when they actually factor analyzed all 28 items of the EBI. The first one was basically a belief in quick learning and fixed ability. The second one was a belief that essentially knowledge comes from omniscient authorities. And then the third factor was a belief in simple and certain knowledge. So that's the gist of the factors. Again, if you go to the blog posting, you'll see how I discuss the minimum loading criteria and using that, as well as how to deal with the negative loadings that you see within this matrix. So we'll scroll down a little bit further. You'll also see a breakdown of the rotation sum of squared loadings right here. So these would be your eigenvalues for your factors following rotation. Now, what happens in the case of Promax rotation, this is essentially an oblique rotation. So what that means is when you first extract the factors during your factor analysis, the factors are uncorrelated. So in other words, they account for additive amounts of variation in your original set of measured variables. If you use an oblique rotation, such as Promax rotation, then what it does is it effectively relaxes that constraint of orthogonality and allows there to be a correlation if one exists, so to speak. So with that, following rotation, in terms of the variance accounted for by each of these factors, then in this particular case, we can't really look at the eigenvalues as kind of reflecting sort of an additive amount of variation that's accounted for, but rather the factors are correlated. So some of the eigenvalues are correlated, so we can't talk about the variance uniquely accounted for by each factor. So that's why here you don't have that information like the proportion of variance or cumulative proportion of variance that we saw previously with the unrotated factors. So these are the eigenvalues that you'll want to report on post-rotation. And then you also have this correlation matrix down here, correlations among the factors. And again, I'm going to defer to the blog posting because again, there were some nuances when I was going back through and interpreting this that needed to be spelled out a lot more than I can really offer in this particular video. The other last example that I want to show you is just using Varimax rotation. So, in a nutshell, I can take all of this same code right here. I'm just going to copy it, paste it in, and just make one little change. And that is, in terms of rotation, we'll change this to Varimax that you see right there. So if we highlight this and click on run, then we get our exploratory factor analysis followed by Varimax rotation of those factors. So really our communalities, all those are exactly the same as before. All of this information is going to be the same. The unrotated loadings and the variance accounted for by the unrotated factors, all that's going to be exactly the same. The difference is that now we've, with this rotation, we've maintained the orthogonality of the factors. So we have only a single structure matrix, or you could think about it as sort of a pattern structure matrix. But basically, with this particular matrix right here, we have just the correlations between the individual items and those rotated factors. And so you can use this matrix to interpret. Whereas previously, when we used Promax rotation, we had two matrices, a pattern matrix, which basically reflects the relationships between each indicator variable or item and the factors controlling for the correlations among the factors. And then there was also a structure matrix. So there were two separate matrices there. In this case, there's only a single matrix that you are interpreting. So it actually is simpler to interpret, but by the same token, you're also making an assumption about the factors being uncorrelated. So if we scroll down a little bit further, you can see too, we've got a breakdown of the rotated sums of squared loadings, or the eigenvalues, and then also proportion of variance accounted for, which we didn't have following rotation using the Promax rotation. So that's just a very general overview of kind of the code that I've gone through, and then just a few additional details that I provided in the blog posting. So please be sure again to go to that blog posting. There's a lot of detail. I think it's a lot more thorough than what I could really offer in this particular video. So at any rate, I appreciate you watching, and you guys have a great day.